Hi there, my name is Mobi Mohoro, and I'm here to present on SIReN-VAEs with discrete variables. This work was done under the supervision of Prof. Steve Kroon at Stellenbosch University. Bayesian networks are widely used probabilistic graphical models which represent probabilistic relationships among a set of variables. For instance, Vito et al. Utilized Bayes nets to model the impact of specific pollutants on various environmental factors and mortality rates. This Bayesian network specifies some of these dependencies. Now, suppose practitioners have access to a set of variables, and they hypothesize that these observed variables in gray vertices depend on a number of latent variables in white vertices, and they specify a Bayes net to indicate the dependencies. In this scenario, they may wish to employ an autoencoder to construct a generative model for the observed variables based on the latent variables, whilst also leveraging information of variable dependencies from a Bayes net. Typically, autoencoders, such as variational autoencoders, or VAEs in short, utilize fully connected networks both in the encoder and the decoder. In the decoder network, for example, this convention implies that each observed variable depends on all the latent variables. But what if practitioners specify a Bayes net, suggesting an alternative scenario, where each observed variable does not necessarily depend on all latent variables? The structured invertible residual network variational autoencoder, or the SIReN-VAE in short, was introduced by Prof. Kroon and Ms. Mittal in 2022 as a model which incorporates Bayes nets into VAEs. This is achieved using novel normalizing flows called graphical residual flows, or GRFs in short. GRFs encode Bayes nets into flows by masking weight matrices in order to encode variable dependencies. The GRFs are used in the encoder network of the SIReN-VAE to infer latent variables conditioned on the observed variables. This is depicted on the left of this figure. They are also used to model the prior of the latent variables in the top right of this figure. The decoder network of the SIReN-VAE is also masked similarly to encode the Bayes net. The SIReN-VAE was originally designed to handle continuous variables, both observed and latent variables. The goal of this research project is to explore ways of incorporating discrete variables into the SIReN-VAEs, particularly discrete latent variables. For this task, we considered two approaches. In the first approach, we investigated extending GRFs to handle discrete latent variables such that they can be used in the SIReN-VAE to infer discrete latent variables. We identified Argmax flows as one approach we can use to achieve this. However, Argmax flows were introduced as normalizing flows which were designed mainly to estimate the density of discrete variables. But our main objective is to infer discrete latent variables. Therefore, there was a lot to consider in order to use Argmax flows to perform inference of discrete variables. And the second approach we considered was based on how discrete latent variables are incorporated into VAEs. In the literature, we found a trick called the Gumbel Softmax trick, where discrete variables are approximated with continuous variables in order to enable propagation during training. We explored using this trick to incorporate discrete latent variables into the SIReN-VAEs. More on this trick in the next set of slides. To illustrate how the Gumbel Softmax trick works, first consider a categorical variable Z with k classes and corresponding class probabilities pi1 up to pi k. The Gumbel max trick provides a simple way of generating a sample of this categorical variable. This is done by first sampling IID G's from the Gumbel 0-1 distribution, adding it to the log of each class probability and taking the Argmax to get a one-hot sample. Zhang et al. Introduced the Gumbel Softmax trick. In this case, they used the softmax function as a continuous differentiable approximation to the Argmax used in the Gumbel max trick. This leads to a Gumbel softmax distribution, a continuous distribution over a simplex, whose sample approximates the one-hot categorical variable sample. The density function of the Gumbel Softmax streak distribution is also provided in this slide. The Gumbel Softmax streak introduces a hyperparameter tau, which governs the behavior of this distribution. As tau approaches zero, the sample generated closely resembles a one-hot sample from the categorical distribution. And as it increases, it resembles a sample from the uniform distribution. In the first row of this figure, the true expectation of the categorical variable is provided. And in the second row, one hot sample is also provided. It can be seen that as tau approaches zero from the right to the left, the sample and the expectation are similar to the true underlying ones. The SIReN-VAE model, designed to incorporate discrete latent variables using the Gumbel Softmax streak, is provided in this slide. In this model, instead of inferring the latent variables directly in the inference network, the anomalized class logates conditioned on the observed variables are instead inferred. This design choice was influenced by a key property of GRFs, which is that they currently stable inversion by placing Lipschitz constraints on the GRF's flow transformations. Therefore, the Gumbel Softmax streak is utilized outside of the GRF. On the right of the figure, the logates are then transformed into class probabilities using the softmax layer. The Gumbel Softmax streak is then employed to obtain the sample of the approximate discrete latent variables. Now moving on to the experiment. The training data used to evaluate if the Gumbel Softmax streak is suitable for incorporating discrete latent variables into SIReN-VAEs consists of 2 categorical latent variables and 5 observed continuous variables. Both the latent variables are binary variables, where the second latent variable depends on the first latent variable, as depicted on the base net on the left. The base net on the right is provided to indicate how new nodes are introduced when the one-hot representation of the categorical variables is used, and it is approximated using the Gumbel Softmax streak mentioned in the previous slides during training. The observed variables are bimodal, as can be seen by the marginal histograms depicted in this slide. These variables are each Gaussian mixture model, where the mode of each is determined by the value of the latent variable it depends on. For example, x1 depends on z1 in the previous base nets in the previous slide. If z1 is 0, x1's mode is around 1, otherwise it is around 10. In the experiment conducted, we are particularly interested in evaluating if our trained models are capable of generating samples of the observed variables whose marginal distributions are similar to those provided in this slide. Moving on to the result. As pointed out earlier, the tau hyperparameter has to be specified in order to use the Gumbel Softmax streak to approximate the sample of categorical latent variables. As tau approaches 0, the samples closely resemble samples from the categorical distribution. For this, we consider tau values less than or equal to 1. For tau equal to 1, the marginal histograms of the samples generated from the resulting model are given in this slide. These results indicate that there is overlap of the histograms of the samples from the true distribution in red with the samples generated by the model in blue. However, for all the variables for this particular choice of tau, the model leads to unimodal Gaussian distributions. We then decrease tau to 0.5. And in this case, there seems to be multimodality imaging, particularly well for variables x0 and x2. These results indicate that the lower tau, which leads to a better approximation of the latent variables, leads to improved results. The tau was then lowered to 0.1, but this led to unstable training. The source of this instability is to be investigated in future work. We also varied the flow steps to see how they influence model performance. And as can be seen, there's not much improvement in performance as the flow steps are increased from the first to the third row. And finally, the Gumbel Softmax tree can be utilized to incorporate discrete latent variables into SIReN-VAEs. The tau hyperparameter has an impact on model performance, where smaller tau, which leads to samples which better approximate the latent some variable samples, improve model performance. In future work, posterior collapse needs to be investigated and addressed to ensure that the model learns meaningful latent representations. Additionally, the instability when training with smaller tau also needs to be addressed. Thank you.